Okay, well, we're going to go ahead and get started. I know there's another phone call scheduled for 9:30 that a lot of folks might be on, so we're going to make sure we get this wrapped up by then. Thanks, everybody, for joining us today. This is our first webinar in a series we're going to be doing here for a little while. Before we get started, just wanted to remind everybody to please make sure your microphones are muted, your cameras are turned off, and if you have any questions during the presentation, just go ahead and ask those through the chat function. Mark Sager is going to be monitoring that. And if he sees any questions that should be answered right away, he's going to let me know. But otherwise, we're going to save the questions for the end. And then at the end of the presentation, if you want to unmute your mic to ask any questions or add any comments, go ahead then. And just remember to have some patience with us as we work through these virtual meetings. As I was getting ready for this, I realized there is a little bit of a lag from the time I update my screen to when you guys see it. So I'll try and remember to go slow and make sure that everything is keeping up with me. So to get things started, I thought it'd be a good idea for people who are pretty new to the soil and water world to do some introductions. And Amy Boyer has put together a pretty nice presentation that highlights the ODA and NRCS engineering staff. Right now up on the screen, you can see our ODA engineering staff. Mark Sager, at least in practice, is our engineering manager. On paper, Terry Mesher is still our engineering manager, but he's pretty tied up with H2 Ohio, and Mark's been filling in pretty nicely for Terry. We also have Amy Boyer. She's our Area 3, Area 5 engineer. She's our road warrior, covers a lot of ground. Justin McBride is our other Area 1 engineer based here out of Hancock County, and myself, Tim Folks. I'm also going to run through real quick your NRCS area engineers. In Area 1 for the northwest part of the state, Dwayne Reithman is our area engineer, also currently our acting state engineer for NRCS. In Area 2, we have Colin Nugent. He's heading up there in the northeast part of the state for Area 2. In Area 3, we have Noah Miller. For Area 4, we have Vic View. And for Area 5, we have Greg Wells heading up the central south portion of the state for NRCS area engineers. And also our NRCS state office engineers, our acting state engineer again is Dwayne Reithman. I invited all of our area engineers to be on the call today. I don't know if any of them were able to join or not, but any of our area engineers or ODA engineers during the call today, if you have any comments or clarifications you want to make, feel free to do so and join in there. And with that, I'm going to jump over here. Take a look at our agenda for today. We're going to try and wrap this up in about an hour. We're going to start by doing a quick review of the current state of the TDP, ADP programs. Then I'm going to spend a minute reviewing some of the ODA training resources that are available. And then we're going to jump into our runoff calculations and working with the EFH-2 software, how to download that software, get the data updated. We're going to run through an example calculation on that, and we're going to do a little bit of comparison of some of the data and results. And then at the end, we'll have a chance for questions on the EFH software or any other questions you might have at all for the engineering technical staff. I'm going to give a quick update on the TDP ADP training. As many of you are probably aware, the governor has asked state employees to continue our efforts to help minimize the spread of COVID-19. That means minimizing in-person meetings and working from home for the vast majority of us. And it's looking like we're probably going to be doing that at least through the rest of this year. We'll see how the course of the virus goes. So unfortunately, we had to make the difficult decision to postpone all of our in-person classes. We feel a lot of our classes and our materials are best suited for teaching in person. So we have that face-to-face interaction where we're able to answer questions, do some hands-on exercises, and go out and do some field visits. So we'd like to try and maintain that structure for most of our classes. And as soon as we're able to schedule in-person classes again, we're going to pick up right back where we left off. We'll get our beginner level courses going again. We'll be offering the grass waterway grade stabilization classes that we had planned for 2020. And our grazing team with Martin Joyce, they had a lot of good classes they were hoping to do in 2020. And I'm sure they're going to be looking at picking those back up as well. So that also applies for all of our ADP classes. They are temporarily postponed for the time being until we can get those rescheduled as well. And anyone that was registered for an in-person TDP class that had been canceled, you should have received an email from me directly regarding whether or not you wanted to refund that class or maintain the registration until that class is offered again. If you think you were signed up for a class and didn't get an email, just get in touch with me and let me know. And if you did receive one of those emails and you haven't responded to me yet, please do so I can get you marked down appropriately. So in the interim, until we're able to do our in-person classes again, we're planning a series of monthly webinars to provide some training opportunities and try and stay in touch and have the opportunity for folks to ask questions. So you can see the schedule there on the screen. We're starting off today with our EFH-2 webinar. September 23rd, we're going to be doing one on evaluating your district's programs. I believe the program specialist will be doing that one. In October, we'll be doing a voluntary nutrient management plan webinar. I'm guessing Kip Studer is going to be offering that one. And then in November, we're going to be doing a state auditor updates. And then along with that, for our APAP class, we're making some changes to the APAP class, and we're going to take the beginner APAP course and put it into an online format. We want to have this basic training for APAP available for new employees as soon as they come on board, rather than having to wait around for the in-person APAP class. We feel this would be a good use of our time to get this one put into the online format, have it available as soon as people come on board. So we're hoping to roll that class out in the early part of 2021. And then possibly along with that beginner level course in the online format, or might be looking at doing an advanced offering for APAP. That would be an in-person class, pending obviously when we can get those in-person classes scheduled again. The other thing to keep in mind is our two existing online TDP courses, the Map Refresher and the Conservation Engineering course. Those are going to continue to be available through March 31st of next year. At that point, we'll probably take them offline just temporarily so we can update the class material as we need to. And then we'll be offering them back out. So that's the current state of the TDP program. Now I'm going to take a quick minute here to review some resources that are available on ODA's webpage. So if you go to ODA Soil and Water Conservation homepage and you come to the toolbar on the left side of the screen and scroll down to where it's highlighted in green resources for SWCDs, click there and you'll end up on this page that I'm on right now. The first tab I want to highlight here is our Technician Development Program tab. It gives a brief description of our TDP program, and more importantly, down at the bottom, it lists all of the courses that we currently have registrations available for. So right now we have a registration form available for our 2 online classes. All of our TDP courses also get communicated out to everybody through a Federation email service. So keep an eye out for TDP updates through the Federation emails, or you can always check back in on our website here. The next tab I wanted to point out was the Administrative Development Program, the ADP tab. You can come here for an update or for some information on the ADP program. Or if you have questions on that, you can contact Cody Hacker at the number there at the bottom. And then the last tab I wanted to point out here was the SWCD Engineering and Technical Assistance tab. This tab has a few links for some different things. you can click on the link to go to the Ohio Drainage Law section. Below that is a quick link to get to the Electronic Field Office Technical Guide. If you're not familiar with this, this is where NRCS houses a lot of their technical information. Probably most importantly to our technicians, it's where you can go and find the conservation practice standards and any of the construction specifications that go along with those practices. And the last one I wanted to make everybody aware of was our DSWC training video channel on YouTube. So if you click on that, you'll end up on this page here, which has about a dozen different videos of webinars we've done in the past. There's a real nice collection of videos where Justin McBride went through in CAD step by step how to design, draw your waterway in CAD. So that's a nice set of videos there. And there's also a set of videos where our former employee Janelle Weiss demonstrated some items in GIS. She showed how to develop watershed maps using the NRCS engineering tools in ArcMap. And those will be some important videos to keep in mind. This NRCS engineering tool for ArcMap is what we typically use to help develop our watershed maps and the different inputs we need to put into the EFH software we're going to be going over here in a minute. One thing to note about these videos is they assume you have a certain level, or at least a minimal level of experience with these programs. If you're opening CAD or ArcGIS for the very first time and trying to follow along with these videos, you might feel a little bit lost. So take a few minutes to get familiar with the programs before you jump right into these videos, or at least be prepared to have to watch the videos a time or two. But those are some great resources there that walk you through some different items. There's also a webinar recorded on here where Kip Studer goes through the voluntary nutrient management planning tool. So those were the different resources I wanted to point out to everybody. And now we're going to go ahead and jump into the meat and potatoes of today's presentation, which is going to be reviewing EFH software. So today we're going to review where to access the software, how to update the rainfall and storm type data, and then we're going to walk through a sample calculation using the EFH-2 software. So what is EFH-2? Well, it's a software designed to calculate runoff volumes and peak flow rates. It was developed using the procedures detailed in NRCS's Engineering Field Handbook, Chapter 2, hence the name EFH-2. So Chapter 2 runoff calculations in the software, they're applicable to a fairly specific set of situations. There's some restrictions on when you can use this software, and we'll cover those in more detail here in a little bit. Today's not going to be a real in-depth discussion on all the calculations and formulas that are covered in Chapter 2 and how they work behind the scenes in the EFH software. Our goal today is to make sure that everyone has the most up-to-date software in rainfall data and cover the basic procedures for using the software. So some of what I covered today may seem a little basic for any of our more experienced technicians on the line right now, but hopefully everybody will find something useful in today's presentation. So what are some of the scenarios where we need to use EFH-2? We might need to use them if we're doing waterways, any grade stabilization structures, such as rock chutes, drop boxes, pipe drops, any spillways from a dike. Basically, any practice where the standard requires that practice to be able to safely convey the peak flow from a given storm event. And you may also be using it if you want to find a runoff volume for storage purposes. So where do you get the EFH-2 software? Well, if you're an NRCS employee or you're on an NRCS supported computer, you're going to go to your software center and you'll see that EFH-2 software shows up there on my screen. It's highlighted in red now, and it's version 1.1.3, which is the most recent version that you want to be using. I am not on an NRCS supported computer, so if you have any more specific questions on that, we'll have to get you in touch with the NRCS folks. So if you're on a non-NRCS supported computer like myself and you need the software, you could do a quick Google search and maybe end up at this page here shown on my screen, and you'll click on the download and you'll see that it's version 1.1.2. This is not the most up-to-date version, so we don't want to be using that. Currently, NRCS does not have the most up-to-date version on a public-facing web page. So if you need that, use the link that I sent out through the Federation email server earlier this week to download the data. And I'm going to jump over to that link now to show you guys that. So this is a file drop site maintained by the state of Ohio. It does have some restrictions in sharing information, mainly that this link's going to expire here in a couple days. So if you don't get it downloaded by then, just get in contact with me and I can resend or update the link, or you can always get in touch with NRCS folks and see if they can get you the software as well. But if you're here on this link, you're going to see 4 different items available for download. The very top one, county.oh, is our precipitation data specific to Ohio. The next one is your actual zip file that contains the software for EFH-2. This is the version 1.1.3, which we need. The next item is instructions for incorporating the updated rainfall and how to get that into your EFH-2 software. I'm going to cover that briefly here in a second. And the type.rf file, which is the storm type data you'll need for the software. So once you've downloaded these files, running the EFH-2 software setup is pretty straightforward, like any other software you need to install. But you'll also need to make sure you save this county.oh file and type.rf file to your computer. And now I'm going to show you where to drop those in on your computer. All right, so you want to come to your file directory and start out on your local disk C. And then from there, you'll want to come to users. And then from there, you'll want to select your username. And then from there, you'll want to go to app data. You can see on my computer, the app data the symbol is slightly lighter. That indicates that this was a hidden file. And so if you're getting on your computer and you're not seeing this file anywhere, it may still be hidden. And what you need to do is go up to View at the top, come over to the Hidden Items checkbox here and make sure it is checked. Once you check that, those hidden files should show up. So you go to App Data and then to Local, and down to Virtual Store, to your Program Files 86. Click on the USDA folder, then you'll come to EFH-2. And this is where you're going to drop in those 2 files, the county.oh and type.rf. Once you drop those in there, or you may need to replace what's currently in there, that'll make sure your EFH-2 software has the most up-to-date information. So for the benefit of the recording, I've got that file directories, file path spelled out here so people can come back and refer to it later if they need to. This is also all described in those instructions, those PDF instructions that were available on the file drop site I showed you a few minutes ago. All right, so now assuming you've got your EFH-2 software installed and updated as needed, you'll be all set to go. So we're going to jump into the EFH-2 software now. Once you open the program, the first item you're going to come to is the Introduction tab. It includes a brief description of the program and also the restrictions or limitations of this program. Real quick, you can see you don't want to be using this method if you have curved numbers outside of 40 to 98. Your watershed acres need to be between 1 and 2,000 acres. Your hydraulic length should be between 200 and 26,000. Average watershed slope between 0.5 and 64%. No valley or reservoir routing required. And our maximum rainfall is 0 to 26 inches. And our urban land use within this watershed does not exceed 10%. If you start trying to enter data into EFH-2 that falls outside of these parameters, you're going to get some notifications. And you may end up with some results that are either less than ideal or just flat out wrong. So if you've got a scenario that doesn't fit into this program, you're going to have to look to a different method. You may need to go to something like TR55. And some of these restrictions revolve around calculating our time of concentration and peak flow. The methods used here really don't apply for some of those calculations if you get outside of these parameters. So just make sure you're paying attention to what your scenario is, and if you're using EFH-2, make sure it fits into the requirements here. So the basic data tab here at the top, this is where the bulk of your effort's going to be required for inputting the necessary data for the program to run. Before I start jumping into any of that, I want to jump into the example scenario we have for today's calculation. So you should be seeing a watershed map on my computer right now. This is for a field just around the corner from my house. If you can see at the bottom of the delineated watershed, there's a existing grass waterway, and upstream of that grass waterway through our watershed, there's a pretty good gully that I noticed runs through that field. So for today, we're going to be looking at using EFH-2 to come up with a storm size for a grass waterway for this area. Now, if you're familiar with the conservation standard for grass waterways, in general, we're going to be designing grass waterways to be able to convey the peak flow from a 10-year, 24-hour storm event. So that's where our EFH-2 software is going to come into play to help us calculate what that peak flow will be so that we can properly size our grass waterway. This watershed map was developed using ArcMap, the NRCS engineering tools I mentioned earlier, and that whole process is highlighted through those videos on our YouTube page. So I'm not going to spend a lot of time today going through how I came up with this map. I'll talk about some of the items individually, but if you want to use that program and those tools to develop your watershed maps and your necessary inputs for EFH-2, go through those videos on YouTube, on our YouTube page. And if you have any questions after that, feel free to get in contact with any of the ODA engineers. But this is the scenario we're going to be working with for our example today. I'm going to jump back to the EFH-2. So at the top of our basic data tab, there's some places just to input your basic project data, your client name, the state. It is critical that you enter your state in here. Obviously, we're all going to be Ohio, but once you enter the state abbreviation in here, it's going to pre-populate this county list with our county data. We're going to be working in Hancock County today. And this is the point where you're telling the software what county level rainfall data you want to use. So if you don't enter in your county, you're not going to get results down the line in the software. We just enter our practice. And then, so the first critical item of information you need to input to the software is your drainage area or your watershed area. If you're not familiar with what that is, it's basically the area where any bit of rain falls within it, it's going to flow to your outlet, your point of interest. In our case, our outlet's down here in the southwest corner of the delineated watershed. So the ArcMap and NRCS engineering tools have delineated the watershed out for me, and it's represented by the red line shown here on the map. So any rain that falls within this delineated area is, in theory, going to flow down to my outlet at the bottom in the southwest corner. Any rainfall that falls outside of it is not going to end up going through our outlet. Now, to use the program, you have to upload some elevation data, typically in the form of LiDAR data. And then the program evaluates the topographic features based on that elevation data and is then able to delineate out what your watershed would be. If you're good with topographic maps, you can hand delineate those watersheds out. And we actually go through that exercise of hand delineating a watershed in our in-person hydrology TDP course. But for today, we've let the computer delineate that watershed for us. And anytime you're delineating out a watershed in the program here, it's always good to go out in the field and verify that it makes sense. There's nothing that's changed or clearly doesn't fit into what was delineated by the program. So we've used the program to delineate it out. It's telling us our watershed acre is 90.2 acres. So we'll come back to EFH-2, punch in our watershed acres. The next item we're going to need is our runoff curve number. I'm going to take a quick second to talk about what a runoff curve number is. So your runoff curve number is a factor used in estimating the potential runoff for a land area. It's based on the soil hydrologic group of that land. It's based on the cover or land use and the condition of that cover or land use. One thing to keep in mind is that higher curve numbers equate to higher amounts of runoff from a given storm, and lower curve numbers result in lower amounts of runoff. So your lower curve numbers will be your soils with higher infiltrative capacity. Your higher curve numbers will be for soil and land types that create a lot more runoff, clays, hard surfaces, that type of thing. The graph shown on here does a real nice job of helping visualize those curve numbers. If you look along the bottom axis, you'll see the rainfall volume in inches. And then along the vertical axis, you'll see the direct runoff created from those rainfall events. And diagonally, you'll see the different curve numbers going across the chart. So let's take, for instance, a 6-inch storm event. So we're going to be looking at the low end of the curve numbers for 40. So if you see the red arrow there, we started at 6 inches at the bottom for our rainfall event. We come up till we hit the diagonal line for a 40 curve number. And then once we hit that, we follow it back across to the vertical axis. And you can see that if you have a land area with a curve number of 40 and you have a 6-inch rainfall event, right about only half an inch of runoff is going to be created from that storm event. So you're dealing with some soils that have a really high infiltrative capacity at this end of the curve numbers. Let's take that same storm event and look at the other end of the spectrum for a curve number of 100. So we follow that 6-inch storm event up to the 100 curve number line. Then we follow back across, and you can see that for that 6-inch rainfall event, all 6 inches have come off as runoff. This is the theoretical maximum end. The thing that could best represent this would be a very flat, hard concrete surface with no cracks or anything like that. You're not typically going to be dealing with land areas that have curve numbers that high. Typically, we're going to be working with curve numbers in the range of 60 to 90 for the most part. So that's what the curve number is. If we look at our watershed map, again, you can use the NRCS engineering tools in ArcMap to help you develop what the curve number is for your area. And so how that process works is you enter into the ArcMap your soil type, and then you also have to designate the different land types or land uses that are within your watershed. So once you put that information in, ArcMap will, the NRCS engineering tools will calculate a weighted average based on those different soil types, different land uses, and come up with a single curve number that represents your entire watershed. And that's important to note because you're only able to enter in a single curve number into the basic data tab. So for our project, we've developed a curve number of 82. So we'll enter that into our EFH-2 software. There's also an option, if you see at the top, there's a runoff curve number tab, RCN. If you click on that, you'll see a table come up and it lists all the different cover descriptions. You have different columns, A, B, C, and D for your different soil hydrologic groups. And you could use this to develop your own weighted curve number. So for instance, if you had 25 acres of straight row crops with a hydrologic soil group of C, you would just enter those acres in. And maybe you've got some small grains on a type D soil. And you can just enter in all of your different information, and you'll see at the bottom left, it keeps a running tally of your weighted curve number as you update it. And it also, I need to update it, and it also tracks your accumulated acres. So you can set it up, you can see the bullet item here, you can set it up to enter it as acres, or you can also enter it in as a % of your total watershed. So you could, if you were to hit accept right now, it would take that weighted curve number it calculated here to the left, and it would go ahead and pre-populate it into your basic data tab. But I've manually entered it here. So our next item we'll need is our watershed length, and we'll go back to our watershed map. Your watershed length is the longest path basically a drop of water could take if it fell within your watershed to travel to your outlet. So again, the tools in ArcMap will calculate that for you based on your elevation data. And it's represented here by this blue line. And it's saying that if a drop of rain fell clear here in this eastern corner, it would follow the longest flow path, which would flow along here to the outlet at the southwest corner. And that's based on the elevation data and the topography of the land. In our TDP hydrology course, we do go through an exercise to do that by hand without the computer, so folks are familiar with how to do that. But for today, we've let the computer do it, and it's come up with a flow length of 4,244 feet. So we'll go back to EFH and enter that in. This information is important for our time of concentration and peak flow calculations. The next item we need to enter is our watershed slope. And probably the most important thing on watershed slope is to note what watershed slope is not. Watershed slope is not the slope of your grass waterway. It's not the slope of the ditch going through your watershed. It's not the slope of the flow path shown here. The average watershed slope is a slope developed by looking at the entire watershed area and averaging out the slope for every piece of that watershed. And there's a couple of different ways you can do that manually. You could use a contour interval length method, which we teach in our hydrology TDP course. You could look at the slopes associated with the different soil types for your watershed and get an average that way. Or you could try breaking your watershed up into smaller sub-watersheds, look at the different slopes of those sub-watersheds and come up with an average that way. I guess right off the top of my head, I'm not sure what procedure the ArcMap and the NRCS engineering tools use. Any of the ODA or NRCS engineers have any feedback on that?
Tim, this is Justin McBride. I'll jump in on that one. It does use a fairly advanced procedure in ArcMap. It basically uses statistical analysis on the pixel size of the topographic information that's inputted, whatever you're using. And it's not simple. It's also not accurate in some cases. For instance, it's typically only accurate within several percent. And the thing we've noticed, particularly up in Northwest Ohio, is that the average slope that the program computes is typically a little bit larger than what we would have otherwise done by the hand method, which isn't really a big deal because it adds a little more, maybe more conservative estimate to the peak flow. But we have noticed that, and that's kind of a result of the process it uses. This was originally developed in Wisconsin, I think, where they have, typical average watershed slopes of 3 to 6%. And so I think that's kind of where it's optimized. But that's not to say that we can't use it or shouldn't use it. It's something to keep in mind, is that may not be the most accurate the flatter you get, particularly up here when we can have, less than 2% slope pretty easily. The other thing I'll mention is on the flow path that the ArcMap program figures out for you. If you see on his screen here, the blue line that's 4,244 feet. It's very nice that the program does that for you, but it depends what version of ArcMap you have. Not what version, I'm sorry, what extensions you have active in the program. So for instance, if you have a license for ArcMap through NRCS, you probably have access to that ability. But if you don't, and your district has its own license, like for instance, I have a license through ODA, I actually don't have access to the extension that will create that blue line. So when you run the program, just know that if you're having errors when it tries to compute that flow path, just know that it's probably because you don't have the right extension active in your ArcMap license. So just don't do that. It gives you the option whether or not you want to calculate the flow path. So if you can't do it, you just basically have to do it by hand. You can measure off the distance. You can follow your flow lines. One thing that is nice is the program does calculate all the flow paths, not just the longest ones. So when you go through it, it'll show you all the little blue flow lines in the field, and you can follow the longest one and get a good measurement on the program. So those are really my two cents on that.
Thanks, Justin. All right, so from our map, it's giving us a average watershed slope of 1.4. So we'll enter that in. And you'll also see in the toolbars up at the top an icon for a slope calculator. If you wanted, you could use that. If you click on it, you get a pop-up for average slope calculator, and then it uses that contour length method. And you would just enter in your length of contours. You have to measure out in some manner or another the length of every contour for your given contour interval. Let's just say 55,000. Our contour interval of 1 feet, and drainage areas are already populated, and we come up with an average slope of 1.4. So you can do it that way. And no, it wasn't just a lucky guess for 55,000 feet. I figured that out beforehand. All right, so once you have these 4 items entered in here to EFH-2, it's going to calculate for you that time of concentration to be 1.33 hours. Your time of concentration, I think I have a slide for this. So it's the time required for runoff to travel from the most hydraulically distant point in the watershed to the outlet. I guess one thing to note, the most hydraulically distant point may not be the most physically distant point, depending on your landscape. You may have a portion of your watershed that, for whatever reason, retards flow quite a bit, and that could be your most hydraulically distant point, even though it may be closer to the outlet. But for the methods used in EFH-2, it assumes that the most hydraulically distant point is also the longest flow path. So you're okay to use the flow length developed here. So that time of concentration is calculated for you. It's necessary for our peak flow calculation. So we've entered in all of our data that we need here. We can now go to the rainfall discharge data tab. And you can see we still don't have our peak flow or runoff results in the columns here. So before those will populate, you need to come up here and select your rainfall type. What you should be using is this NOAA type A, and I'm going to talk about those more in a few minutes here, but just be sure that that's what you're selecting for the time being. Once you click on that, you'll see that your peak flow results and runoff results now populate into the table. So in this first column, you can see is frequency. That's your storm event frequency in years. So 1 would be a 1-year storm, all the way down to the bottom, which would be your 100-year storm event. Your second column is the rainfall precipitation amounts associated with those storm events. One thing to note here is you can manually enter in different rainfall values here if you wanted to, and it'll calculate new peak flows and runoffs from that. And if you were to do that and you needed to reset it, you would just come up to File and hit Recalculate. If for some reason you had a certain precipitation amount you wanted to punch in there and see what results you get. And then our third column is that peak flow result, and our fourth column is our runoff amounts. So you can see for our grass waterway, we were interested in the 10-year storm here. It's telling us that our peak flow is 77 CFS and our runoff amount in inches is 1.77. Once you have all this, you can come up here to the top and hit the print function, and it's going to create a nice printout. And I'll show you the printout, what that looks like.
Tim, this is Mark.
Yeah.
Jay has a question. He asks, is there a way to add the NOAA-A data? It's not available on his dropdown.
That's part of updating the rainfall data that I talked about earlier. When you go through that file path and add those files in there, once you've done that correctly, those rainfall amounts in the county in the dropdown will change to that NOAA type. So let me jump back there. Back on your basic data tab in the county, if you're seeing this NOAA type A, that means it's been updated. And if you haven't, either when you drop the files in, you didn't get it in the right spot, or you just haven't done it yet. All right, so back to the printout that's you get from the EFH software. At the top, it documents your client project information. Here in the middle, it documents all of your inputs that you use to create the result table at the bottom. And you can see your frequency here in the first row, your runoff amounts show there in the middle, and your peak discharges get tabulated in the bottom row. So it makes a nice report that you can put in your file for your project. So that's pretty much it for how to actually use the software. We got about 15 minutes left here. I'm going to jump over and talk a little bit more about the rainfall types and the different rainfall data. All right. So there's two things that we loaded into the software. We updated the rainfall precipitation values, and we also updated the data for the different rainfall types. The old data was the NOAA TP40 or technical paper 40 data for rainfall. That dates back to the 60s or give or take. And the rainfall types that were developed for that rainfall data were the old type 1, type 1A, type 2, type 3. These rainfall types are specific to geographic areas. And in Ohio, we would always use this type 2 rainfall event. And I'm going to talk about these more here in a minute. This is type 2 is what we used to use. The new data for precipitation value comes out of NOAA Atlas 14 Volume 2. And actually, it's not really all that new for Ohio. The Volume 2 came out about 15 years ago. And actually, I'm guessing that everybody's EFH-2 software probably already had this updated rainfall precipitation data. In fact, if anybody thinks they have EFH-2 with some older data in there, shoot me an email. I'd like to find out some more about that. But I believe everybody probably already had this updated NOAA Atlas 14 data for rainfall values. What we were probably missing for the most people was having the correct rainfall type or storm distribution type, these NOAA's type A, B, C, and D. Ahead another slide here. So for Ohio, like I said before, those rainfall distribution types are geographic. For Ohio, we're going to be this type A. You can actually see there's a few blue spots on this map that show type B, but our state engineer has indicated that we should all just go ahead and use that type A storm. So what is a rainfall distribution type or your storm type? Well, they describe over time how the rain falls for a given storm and the intensity over time. So if you look at this graph here, you can see on the bottom is time, 24 hours. So we're looking at a 24-hour storm event, and on the vertical axis are these cumulative percents of rainfall that have fallen. So at the bottom, at the start, 0% of the rainfall has fallen, and as we work our way across and get to the top, at the end of our 24 hours, we've hit our total rainfall accumulation. So like I said before, we used to always use this type 2 storm, which is shown in the red line here. And now we're switching over to this region A storm type, which is this darker blue line. And so let's take a look at those and kind of evaluate the differences. They look pretty similar, but they're slightly different. So if we were to look at the old type 2 from 10 to 14 hours, we would find that roughly 65% of the rainfall is falling within the middle of that storm period from 10 to 14 hours. Now, if we were to compare that in the same time frame for the newer region A rainfall type, we would find that about 72% of the rain is falling in that same period. So what that's telling us is we're getting a little more rain in the same period of time right there in the middle of the storm. So it's a little higher intensity right there in the middle. And what's that mean for us? Well, it means we're going to see a slight increase in our peak flows when we switch to this rainfall type. And if we were to compare that, these are the results from the example problem I just did. The type 2 is the box at the top, and you can see our peak flows generated from using that type 2 rainfall. For our waterway in question, The 10-year storm amount was going to be 72 CFS for the peak flow. Now, if we compare that to the new NOAA Type A rainfall distribution, you're going to see those peak flows have jumped up just a little bit. Depending on your situation, your peak flows are probably going to go up somewhere 6 to 12%, give or take, depending on your specific scenario. For this case, our 10-year storm has jumped up about 5 CFS. So that is the main effect of that new storm type that we're using in there. That pretty well concludes the presentation I have, and we're about out of time. Hopefully we take a few minutes here for any questions. Mark, we got any on the chat?
I do not have any in the chat, so if anyone would like to ask a question, unmute yourself and ask away.
All right, well, hearing no questions, if you do think of something later, feel free to get in contact with me. We'll get this wrapped up for the day so folks can get on their ever call. Appreciate everybody joining us today for the call. Tune in for the webinars we have coming up. Thank you.
All right, thanks, Tim.